All right, so I want to give a little history to artificial intelligence, partly because I get mad because the stuff I did in AI is like totally forgotten about now because it's this whole little niche area that's become all of AI. So my first question to y'all is, anyone recognize, a little blurry, but recognize this image in the background? You can type in the chat. What is it, Michelle and Hector?
Is it Hal?
It is Hal. So if anyone has seen 2001, this is Hal's eye or sensor that they made look like an eye, but it's a camera basically where Hal is getting images from the movie 2001: A Space Odyssey. Go ahead, next slide. So this term artificial intelligence was actually coined well before that movie that came out in 1968. Coined in 1955 for a conference that was held in 1956 at Dartmouth Summer Research. They called it the Project on Artificial Intelligence. A fun thing is these are the four main people, McCarthy, Minsky, Rochester, and Shannon, who coined that term. They are all pictured at that conference in the upper picture. And then some of them are pictured later from 2016. I couldn't tell who the first person was in the newer picture. But what I think is interesting from here is where these people were. Besides Dartmouth, where it was held, there was a Harvard person, Marvin Minsky, who was at MIT when I met him and brought him here. I think he was there, not Harvard anymore. Rochester was at IBM, and Shannon was at Bell Telephone Laboratories. I got to work at IBM one summer, and I got to work at Bell Telephone Laboratories for 2 summers. So I got really great connections with some of these places where this stuff started. And I wonder, one of the things I wonder about today, go ahead to the next slide. I wonder about today is, where are the Bell Labs of today? There's Google, that is definitely in the virtual world of things, but there really aren't many places left that are like the Bell Labs that did exploratory brainstorming kind of research and put a lot of funding into it to find things. And there are many, many things that were found at Bell Labs, like the background radiation noise from the beginning of at the start of the Big Bang, and that sort of thing was theorized and proved there and other places as well, but really started there. So anyway, artificial intelligence came from and has come from many, many different areas. So it's a mix of capabilities. There's some of the skills that are kind of artificial intelligence skills in the middle there, those middle 2 boxes, but what's needed to do those things has been pulled from computer science, mathematics, cognitive science, psychology. In fact, I got into this field in 1978, summer of my junior to senior year at University of Michigan. I was given the book that's pictured on the right there by Patrick Winston, who was pictured in one of the previous pictures. I was given his book as a birthday present. I was so mad at my friend. He gave me a textbook for my birthday. I'm like, what are you thinking? But the thing is, I looked at it and I started reading it. I wasn't in any class, and I started reading the thing. And that's how I got into artificial intelligence. Go ahead to the next slide. And that's how I found out I investigated, found out there was a professor at University of Michigan at the time who had got his PhD in AI from Stanford. And I did a 1-credit independent study in engineering about artificial intelligence. And I read 3 of the top books at the time and did like book reports and had conversations with him. And that was my only engineering course in my undergraduate work. And I went on to a PhD program in computer science and engineering at the University of Michigan because I had all the math I did. It wasn't willy-nilly, but I was led into an engineering PhD without an engineering background. But that's how I was allowed to get into and start studying artificial intelligence. And then I did game playing, which I'll talk a little bit about, of game playing in AI. When I was at Southwest Research Institute, actually working in the artificial intelligence group, we actually had a definition of artificial intelligence as the area of computer science that attempts to provide computers with the capability to solve problems that would otherwise need human beings. AI really had gotten a bad rap in the 1960s because a lot of those people from that conference actually started touting that, oh yeah, we'll have language translation solved within a couple years. That didn't happen. So AI started out with kind of a bad reputation, but then I think made up for it later on. And, now we have pretty good language translation. It just took a lot more than they thought it was going to take. I like to say that artificial intelligence is about making computers do things that look smart or intelligent. And in fact, I don't care how that happens. It could be with AI techniques or not AI techniques, but we make a computer look like it's solving something that would require some intelligence. Now, we have to define intelligence a little bit for that one, but that's how I talk about it. And I have friends at Boeing who used to talk about they want to make HAL from the movie 2001, which is why I put the HAL there. And that's what a lot of people had thought about AI. That was, I think, one of the, a front science fiction AI character that unfortunately was bad, because if you haven't seen the movie, it's worth seeing the movie for a couple things. One is the view of what computers could do. And there was a problem. There were conflicting kind of goals for Hal. So Hal got into trouble and got a little schizophrenic, we might call him, that happened, and then did bad actions that he shouldn't have done. And the movie itself, a space movie, actually is one of the first movies and one of the only movies, besides Gravity is another good one at this, that doesn't show noise in space. So it's a good movie to see for a couple reasons. Go ahead to the next slide. It is a little slow on action in today's terms, but if you realize it was made in 1968, you should be fine. A simplistic look at what's the difference between AI and conventional programming. If I were in the room, I would ask, who knows, who has done any kind of programming, conventional programming, Python, Java, C, C++, any kind of thing like that. So you can raise your hand for yourself. Or you can raise your hand if you want with the reactions. Do we have the reactions available? If you want, you can raise your hand. But I want you to remember, what that kind of programming is like, where you get data and you make decisions on it, and you have conditions about if something's true, you do the set of things, or you may do a set of things multiple times, loop through them. AI is different in general. Again, this is very simplistic in that we have a problem as input, and then we have a bunch of possible, think of them as small routines that could be accessed, could be activated, but you may go back and forth between them. You may go up and down, you may move around. So there's not quite a linearity to it that we often have in conventional programming. And we come out with some solution that usually is some percentage known to be correct. So it's usually not 100%, whereas with our conventional programming, we are pretty sure that it should be fairly good. Go ahead to the next slide. There have been lots of subfields within artificial intelligence, and really still are. When I was working in the area in the mostly late 80s and early 90s, we made expert systems at Southwest Research Institute. I made on about a dozen teams making expert systems. And then I did my PhD work in game playing. And if you just get a glance at these different areas, that neural networks, that's mostly what we hear about now, and the speech and language processing. Anyone ever get to use an OWL, that on the right there, that speaker that will follow, speaker and camera system for a room where you have lots of presentations, that OWL will follow the speaker around and has a little bit of AI in it, a little bit of rules. A number of home appliances have had AI, very simple rule things in them since the 2000s. Go ahead to the next slide. What I like this image from the AAAI, which I'll have a slide about that organization at the end. This is from 2010, and it even says then the AI landscape is always changing. But what it points to is all the different things in someone's home that could have AI in it. And that was in 2010. So it's gotten more, right? All of our assistants, Siri and Alexa. I have my Alexa computer because of Star Trek, by the way, but we get in trouble because we're a techie home. So whenever we say computer, she thinks we're talking about her. Go ahead to the next slide. So again, I was at Southwest Research Institute from the mid 80s to the mid 90s. See, and it is an independent nonprofit applied engineering and science organization that has some similarity to Bell Labs, but most of its funding is from organizations hiring them to do things. There's a small percentage that's put into internal research and development, but it's very well defined. So I don't think the Bell Labs part is going to be here, but there are some cool things that have come from Southwest Research Institute. It's definitely something, a place worth looking into. They have a little museum there. Unfortunately, the campus is now closed unless you have an invitation or are on a list. There are amazing things, though. If you can get an invitation in, there's a rare books collection. You can go and with gloves touch these books that are really, really old and by scientists. And again, there's a little museum they have that talks about things like woodpeckers. Connects a couple things for me. Woodpecker repellent was created at Southwest Research Institute by materials people for the telephone company, because woodpeckers would, peck on telephone poles and that'd be a problem. Go to the next slide. Whiteout was invented there and other things. So in the 80s and 90s, these are some of the things we did and what a lot of other different organizations did. I think thinking about it now, I probably should have listed other organizations that did AI, but really any kind of large organization that did anything techie had at least one and sometimes a group of people doing some artificial intelligence. We used to compete with large places, Lockheed Martin, Boeing, thinking of the space ones right now. But anyway, IBM and other CAIC, other organizations did AI. These are some of the things that were very successful. Diagnosing something and classifying a thing was very common to have a little expert system put together or a little piece of software to be able to do that kind of activity, solve that kind of problem. Go ahead to the next slide. You can see robotics is even there. As you go to the next slide, Southwest Research Institute made a paint stripper and a robotic derivator that usually has to have a human being do it, but they made hardware and software to do that. So knowledge representation is a big deal. How do you represent what you know? Think about it for a moment. Think of all the things you possibly know now and could maybe know. How could you represent that in some way, like a big long list of things or a table, or how would you connect those things? And that is what your brain really does. So the idea of neural networks is this idea of using the neurons in your brain as a node to represent something, and the neurons in your brain are firing, so they're like zeros and ones. But when does it fire? Well, there's some threshold value that has it fire, and the same thing for nodes in a neural network. So we're trying to use neural networks to represent knowledge. It takes a lot to do that, though. And there's shortcut ways, which are listed there. You can have models, you could have rules, you could have cases, you could have a blank slate that you're filling with facts. And those are other possible ways to represent knowledge. Go to the next screen. These actually were from pages that were used at Southwest Research Institute. One of the things I got to work on was intelligent tutoring systems. So we made tutoring systems, and I thought it was appropriate since we're talking about in education here. I have helped make tutors that were smart in terms of, based on a student's responses, would automatically remediate to the appropriate place that it looked like they didn't understand something. So this was actually for Johnson Space Center, this particular tutor listed there. for Johnson Space Center to train how to use the propulsion console for the space shuttle. So this again was from the late 80s. So the technology they were using was from the 70s. Go to the next slide, but was a successful area in AI. In general, when we were making expert systems, it was considered a spiral method or iterative approach that now is all the rage because it's an agile approach to software development. If you understand that, great. If you don't worry about it. It's now a very common approach to software development where you analyze a little bit, see what the problem is, write a little bit of code, you test that out. Does it really answer what we want? You go back and analyze again and maybe make a few design differences and you test it out, write the code, test it out. You go through a loop like that. Expert system development has always been like that. Common tools are listed on the bottom there. We used a free tool made at Johnson Space Center called Clips, but Lisp, Prolog, Key, Art, M1, and some other tools were very popular at the time. Go to the next slide. There are tons of ways to reason. If you think about all the different kinds of reasoning you do, I'm going to teach a class for Upward Bound at 10 o'clock that is about different kinds of thinking we're going to talk about. So we also have different ways to do different kinds of reasoning with computers. And these were some that have been popular over the years, but you can see the ones that I primarily focused on were rule-based reasoning, most successful in the 80s and 90s for AI. And it's now shifted to the neural networks and this idea of deep learning. I'll define a few of those things and you'll see some more details about it later. Go ahead to the next slide. So I asked you about how could you represent what you know. Here's a set of ways that we can represent knowledge. I mentioned some of them. And you can see there's other things there, just even logic, plain old logic. And there's ways you can symbolically manipulate logic that are pretty cool. I met the guy who started fuzzy logic, Lot Fazati, once at a seminar, and then genetic algorithms isn't here. I actually had the guy, John Holland, who made genetic algorithms for a class at the University of Michigan. He was on my PhD thesis committee for a while, and then Los Alamos scarfed him away, so I lost him. But part of my point in mentioning it and presenting those images to you from the 50s is this field is not that old, and there's still possible to meet some of the pioneers from this world. So if it is something you get more and more interested in, it's, you can go to conferences, AAAI, again, I'll mention that later on, conferences and that sort of thing, and meet some of the people. So neural networks is the main piece about neural networks is what it's doing is recognizing patterns, which is really all your brain is doing. I always get left with the question, though, when does data become knowledge or information? So we could have a set of data. How do you make it knowledge? If you just make a connection between two things, is that knowledge or information? And no one's really answered that well. Go ahead to the next slide. So one of the things I have looked at over the years is what are the ways we can learn? And these are just some of the ways we could have a computer learn is take advice, in some cases, maybe new case analysis or new rules, learning from examples, which is one way neural networks learns, is we give examples to a neural network that is training it, and then we have a neural network decide, is it that thing or not? Is it similar enough to my training things? Or by problem solving, where I'm trying to find and apply rules into new situations and maybe even come up with new ways to think through something, and which is also a little bit of discovery, trial and error, where we have kind of heuristics, rules of thumbs to follow. Go to the next slide, please. So in AI, we've had different kinds of learning. Again, the focus now is this neural network, but there really has been pruning, which is we have a program work on a problem and play a game, for example, many times. And when it loses, it cuts off that branch. I'm not going to go down that way anymore. Think about when you learn to play tic-tac-toe, for example, you would play with someone and go, oh, I lost on that. I'm not going to do that thing right before I lost. and that's kind of pruning learning. Or you could add new rules into something, taking advice from someone. I'll talk about the last one. Genetic algorithms is really a trial and error learning, which is how genetics works through mutation and crossover. Same thing applies in the computer science world. We apply those biological learning modalities into computer programming. And then lastly, coming back to neural networks, is learning by being trained and some trial and error, getting feedback, by matching patterns. And that's the main thing I'd want you left with about neural networks. It's always doing pattern matching. Go ahead to the next slide. So I want to talk just briefly about AI in gaming, because that's one of the places I know about. Again, I developed a theory for a computer to play multiplayer games well, and combined artificial intelligence with game theory. That was my thing, mathematics, right? So I developed an algorithm, and I proved that that algorithm would find you a solution that was good in the game theoretic sense. But just a little history again to give you the history of AI in gaming. In 1963, that's a while ago, and near the beginning of AI as it's thought, right? So Samuel made a checker player that was very, very good in 1963. There's now a checker player called Chinook that actually is touted to have solved checkers. What does that mean? That means if you were to play Chinook, you would at best tie or lose. And it did things that are listed there. There are techniques from AI that some of those things are applied now into neural networks. So iterative deepening is the process of going, okay, I got this far looking to this place. Let me look a little more ahead and do the same sort of thing again and see where I get. And then it also had what are called heuristic evaluation functions, where I take a state of the board of checkers and go, okay, how good am I at this position? And it's usually a rule of thumb for how do I tell how good I'm at this position? Same things going on in neural networks, where there's a kind of evaluation of, how much am I certain that I found the letter A is a common example used. Then there are these other people. Again, I know Hans Berliner did a backgammon player, and Wilcox I never met. I think I saw him, though. He was at the University of Michigan where I went. And chess by Shannon, that Claude Shannon, same Shannon, started doing a program in the 50s before AI was coined as a term. And then lots of characters have been AI agents in video games. I'll scroll through those. Go to the next slide. I'll show you some very briefly. After I tell you, the most success came in 1997 when Deep Blue, made at IBM, beat Kasparov. Yes, Garry Kasparov, you may have heard his name in the politics in the Soviet Union in Russia. He was high up in politics there, partly because he was well known for being a chess player, but then he got more well known for being a politician. But another interesting thing here, I worked one summer at Lawrence Livermore National Labs and got to meet Harry Nelson, who worked on the Cray Blitz, a precursor to Deep Blue. But Deep Blue got beat by Deep Fritz in 2002, and so on, and it continues. They still do play games against computers to see how well people do against computers. But that was a big deal in 1997. Go ahead to the next slide. And again, this is just a list. I don't expect you to see any of these, but the point is there's a lot of them, that these are games with some AI in it. So if these are games with some AI in it, just think about other things in the world where there is a little bit of AI in a fair amount of things that you have access to. Again, you could think of that picture of a house from the AAAI 2010 conference. Go ahead to the next slide. There were specific kinds of techniques in these different games. The one I want to point down to is there was some neural networks already in dirt track racing and fields of battle. Never played either of those games, but they existed. Some of the other games you might have seen, Civilization's been around, The Sims has been around, Quake has been around. Quake actually had some AI put into it by a professor I knew at the University of Michigan, John Laird, who wanted to get some real AI into this gaming world because it was mostly fledgling AI stuff. And so he was very successful at kind of bridging those two worlds. Go to the next slide. I want to tell you briefly about an expert system that I worked on, just to give you a sense of the kind of depth that there was in expert systems. I did a project at Southwest Research Institute called the DRAIR, Deficiency Report Analysis Information Report. Yes, we know report was in there twice, but we could pronounce it. I think that was why we picked it. It was for Tinker Air Force Base. We developed it at Southwest Research Institute. We actually had two contracts to develop stuff, kind of a see if we can do it, and then one that became full-fledged, had its own database number with the United States government. So really quite a wide range of work that we did. The subtitle I gave to it is Parts Gone Wrong. So the idea, go ahead to the next slide while I talk about it. The idea was there were analysts at Tinker Air Force Base who were overworked from other people who were responsible for specific parts on aircraft. So these are about parts on aircrafts. And they were seeing potential issues and wanted to get all this data that we knew was around all different places in the United States, Wright-Patterson, other places. And they wanted to get reports about, hey, I'm seeing something here. Is it true? Is it real? And then these analysts would take about 1 to 2 weeks to actually pull the data together, take a look at it, analyze it, and put a report together. We wanted to reduce that to a day. So the idea was to be able to get that data in one place and have the reports be consistent, have certain parts to it that said where the data was from, and be able to do that in under 8 hours. That was the goal. Go ahead to the next slide. So we created a prototype. We had inputs into our product of what the end aircraft was, like an E-3 or a C-135 or a B-1 bomber, what the national stock number of that part is. Every kind of part has its own national stock number, and whatever work unit code was, I don't remember even what that was. We took 3 inputs. They had no problem with those 3 inputs. We wanted to summarize the data, analyze it, and make recommended actions. Go to the next slide. So again, this was over a multi-year effort. In general, we had to pull all those pieces of data together onto one machine. I'll never forget, we were at the basement of Tinker Air Force Base, mile-long building, counting up how much data we were going to have to store on our machine. This was in 1988, and we counted it up to Pam Fink was my boss then, and she had a clipboard. I remember her writing on the clipboard. Remember those, those times when you go, oh, wait, it's one of those moments where I can still see her writing on the clipboard. We needed 1 gigabyte to be able to be held of data on the machine we were going to do this processing on. We didn't have a machine that held 1 gigabyte in 1988. We had to buy a new machine. So another thing to point out is how much things have changed. I carry around a 128 gigabyte little keychain thing. Can I even get it to show? If I did my back. Anyway, it's tiny. It has 128 of those gigabytes. So anyway, we pulled a lot of data in from different systems. Go ahead and go to the next slide. And a lot of reports that did already exist electronically. We had to get this new machine, a DECVAX at the time, pull into a new database tool, Unify. We used C, the C programming language. We used that CLIPS rules. I want to show you a specific rule. Go ahead to the next slide. This is an actual rule from that system. And if you can see a little bit of the text, I'm defining a rule. We gave a number to it, and then there had to be a bunch of things that were true. These are the conditions. If these conditions were true, then we're going to do the set of actions that are in the second set of lines. But that first set of lines, those conditions were made true based on the data. So there's a whole other set of rules that said if the mission capable hours were between this range, then the mission capable hours are considered high. Or if the depot repairs were this range of values or numbers, then it was adequate. So a set of rules had already been applied to come up with these conditions that the goal is my actions recommended. I want to get some actions recommended. The maintainability is considered okay or high is how to read that. The reliability is low. The supply is not okay. The mission capable hours is high. The depot repairs is adequate. The depot level has a shortage. If all those things have been analyzed to be true, then we would put in our report this set of sentences. There is a short supply, or the parts are not at the right place. The location of the asset should be determined. So then we can make other recommendations. So that's an example of a rule. There were hundreds of rules like that. Next slide. And just imagine all those rules possibly firing then produced a report like this, which I'm sorry is a little too hard to read, but I can tell you about the sections. There was the basic information about what aircraft. This was about the B-1 bomber. We gave information about each place where we got data. That's the next paragraphs. Go to the next slide. More information about where the data came from and what these other reports said. Go to the next slide. We put all these sentence by sentence together from the expert system. And then the last two paragraphs were again put together sentence by sentence by those rules. So you can see, I'll read a little bit of it. The reliability of the listed B1 items is decreasing relative to the low mean time between maintenance. Most problems with the electrical system are electronic failures. So that should tell someone we should look at that. Typical relays, circuit breakers, or SDMAs have gone bad. There appears to be a shortage of assets at the base level. So all this analysis got put together based on those facts, conditions that were really put together, and then potential actions were recommended. We used to joke about making the action recommended of grounding the fleet, but we never did that. Next one. So again,
before you continue, Hector has a question.
Please, I'm sorry, yes.
So that report, this is kind of important to what's going to be happening in the next couple hours. So that report that you just showed, so you all wrote the report based on the data, or it spit out the report as is?
It spit out the report.
Okay.
That report was automatically generated. And here's the cool thing. It was automatically generated within 8 minutes. What we wanted to be done in less than a day of work would get spit out within 8 minutes. It went through collecting that data, hundreds and hundreds of rules applied, and that report was spit out that way.
And thank you.
Yeah, thanks for asking, because again, it was one of the most successful expert systems I got to work on, and it got its own DO something number to it. If anyone's worked in the Air Force, there's the DO 56 is the maintenance actions on every single aircraft part that has a maintenance job done on it. There's a entry in the DO 56 database, which we pulled data from, by the way. And then this tool got its own DO number. Yeah, good. Any other questions? I'm sorry, really, if anyone has a question, let me know. Okay.
That's the question at this time.
Okay. So what we have more available to us now are things like dogs and R2-D2s and dancing robots. And then I wanted you, could you go ahead and click on the humanoid-like link and scroll through just to get a sense for now. I don't know if you guys were going to get into this at all. Were you going to get into this?
No.
Right? Yeah. Okay, great. Let's kind of scroll through and just get present to what is currently available to us. They're pretty creepy, if you ask me. You can scroll through them pretty quickly. I don't think we need to land on anything. Japanese one. And they all do different kinds of capabilities. There's not any one like all acting agent yet. A good one that runs well, one that keeps balance well. Maybe medical ones will get some robots for agility. Again, some creepy ones that have good expressions on their face. The people in China working on that one. Again, this one looks really creepy to me, but I don't remember what that one does. Underwater robots, yay. There are potentially ones to, for elder care and youth care. Pepper is the one that I've heard of actually in industry. We're going to see more and more of them. Of course, doing physical maintenance. Great, thanks. That's plenty. So let me say I have a couple slides about neural networks. I don't know that we need to watch the videos unless you guys are going to get into what a neural network is. Is that right?
We'll be getting into basically how it works with ChatGPT, and but not in the specifics. But as it pertains to education, we're going to cover it at a very high level.
Okay. I don't think we need to watch the links, but you guys, anyone could go out there and look at the links. If you could put my slides back up. So there are 2 links in my slides that has the next slide about artificial neural networks, but the pictures kind of say it all. And then there's terminology over on the left where there's layers of these neurons, of these ons and offs. There are thresholds that has something fire or not. Again, think a little bit about it works like neurons. There are weights of importance. You put training data into these sets of outer layer neurons and inner layer neurons, and imagine you have millions and potentially billions of these things. Then there's different kinds of networks. A convolution just means there's multiple functions. A recurrent neural network just means there's feedback of, we found one thing, let's feed it back in and see if we get something else, sort of thing. Deep learning kinds of networks have lots and lots of layers. And then there's times where you have supervised, where a human being can intervene, and unsupervised, where you kind of let it go and see what you get at the end. So there's all those different terms that can be thrown around if you got into the deepness of neural networks itself. Go ahead to the next slide. Just again, think of millions of nodes and connections. We've got inputs into these nodes and connections that may have weights with them that can get changed based on how it's training and learning and seeing new examples, and then outputs or actions into the world. So I like this particular slide as a way to think about a neural network, but it's millions of nodes and connections. Okay?
Dr. Redfield?
Yeah.
If you could go back one slide, I wanted to mention something to everybody.
Sure.
While as you look at this neural network and you see the bullets over here where it talks about predictive, weights and importance, recurrent and deep learning and training, those are words that you'll hear again and again with ChatGPT that we'll work on. ChatGPT is not solely an artificial network. It's based on other things as well, but it's good to kind of get that into your head, because one of the big reasons that Dr. Redfield is here to help us with is because the last thing I wanted people to think about when they look at AI is that it's somehow magically doing these things.
Yes.
It helps a lot to see all of these pieces in the history of it, so it doesn't feel like there's this almost magical thing that's happening overnight. And no, there's been all sorts of work that's been done here. And the nuts and bolts things really helps us, because when we first look at it, it really looks like magic. So that's Dr. Redfield's been very kind to show us all this information, but I'll hush now.
That's awesome. No, it's perfect, because it's funny. One of the slides we used to show when we went, go ahead to the next slide, even the one after that. One of the slides we used to show when we went to NASA and other places talking about AI was, it's not magic and it's not a panacea. It doesn't solve everything. It really is some programming and modeling, right? Another way to think about it. It is going to be interesting because the machine instructions per second that a human being has access to, we're getting pretty close to being able to do that. So I think that's one of the reasons things are starting to happen, is we're actually starting to get to the place where there could be some similarities to how we solve problems. I don't think we are anywhere near that, but there could be, right? Just with the sheer numbers. Go to the next slide. And there's some links here for some of these things. Oh, I thought I took that earlier one out, but I guess not. This is just the growth of computers and computing, and you can see if we're on this exponential trajectory, we'll get to human being pretty soon. Go ahead. And then another time when I'm back, if we have a kind of break, I can have a fun talk that I do about artificial intelligence in fiction. Like, can we do that AI that we see in these? These are some of my favorite shows where we can see AI, and pretty much we can't do them for the most part. Go to the next slide. So here is that organization, AAAI.org. It stands for the Association for the Advancement of Artificial Intelligence. When I joined it, it was the American Association of Artificial Intelligence, but so many people were members from outside the United States, they finally changed it to a better, more appropriate name. And I love the comments now I'm getting to look at of someone did Upward Bound, yay. So the thing I want to talk to you about, so if you're interested in this, AAAI.org is the place to go check out. And yes, that other film, Ex Machina, or however you say that correctly, is a good one to see, although a little disturbing. I'm teaching for Upward Bound, a course I'm calling Puzzles, Games, and Mysteries. And I put into ChatGPT, I asked for a lesson plan for 11 sessions to teach about how to solve puzzles, games, and mysteries, and including puzzles and games to use in each session. And it came up with pretty generic stuff, but it did have about half the puzzles and games that I was already planning to use. So I thought that was very interesting. I thought I would end with a little exercise that Michelle, you can maybe make it so that we can write in this doc, and we just click on that Google Doc. Has AI done and can do now? What do you think AI has done, and what do you think AI could do now is the question. What have you seen, or what do you think? Oh yeah, I think AI can do this. I think it's always interesting to see what people think. A simple parallel example is, I remember must have been 2010-ish when the first Dragon launched by SpaceX, the first commercial space launch happened. And I announced that at John Jay Science and Engineering Academy. I was speaking to the new graduates, and I announced it was historic that the first commercial space flight was happening. And the kids were not surprised at all, because they thought we had already been doing it. They didn't know that hadn't happened yet. It all had been by the government. So anyway, it's always interesting, right? What we think AI can do. You can put your name to it or not. You can be anonymous. I don't care. I've used AI for starting ideas of lesson plans. I know that Susan Reeves does that a lot from Region 20. Improving writing skills. Oh, avoiding passive voice. Nice. I have had students use it for debugging. I'll put that. Debugging computer programs. It is not great at just straight out writing them. I've used ChatGPT to try and write some code, and it hasn't worked for the most part. And it's not well commented, which is horrible programming. And it does very unconventional things for no particular reason.
I gotta disagree. I got it to do some really interesting stuff, Carol. I was really shocked.
That is great. I've seen some good things, but I went in and asked some really simple stuff, it seemed to me.
I,
So
I
I've,
asked,
I've seen both.
I asked it to do in JavaScript to go and basically scrape the internet and on a certain topic. And when it got to a place that it wouldn't work, I asked, "Why isn't this working?" And it took me back to what I needed to do on my end to get it to work.
Yes. So collaboratively is how we should be using it, just like you said.
It was,
right?
I was just totally shocked that it was able to do it, because I'd never experienced. There was something that I needed to do, and it would have probably taken me 3 days. I didn't.
Right. To learn that, right? I wonder if it's better in some languages than other. Like if it's better in JavaScript than C. That could be interesting.
Yeah. Java.
Now, did it include comments in the JavaScript?
It did in JavaScript. It included comments, and in
that's great
and in Python too.
Nice.
Yeah, it do that. And C, I can see why.
Yeah. So it might be some languages, but so I think a lot of our points today are going to be whatever, use it collaboratively. Whatever you're going to use, you need to verify it. You need to double check it. You need to do your own critical thinking.